Hello everyone. It has been an eventful day. You must be enjoying sessions back to back. And today I will talk about vector embedding and pgvectors. In this presentation, I will cover vectors, basic, vector embedding, vector databases, and pgvector. So let's fasten your seatbelt and be ready. Before we jump into the topic, I would like to introduce myself. My name is Ninad, and I have been working with Percona for the last 3.5 years. My overall experience is 18 years, and during that period, I worked with various database products like MySQL, Oracle, Postgres, MongoDB, and others. From last 1.5 years, I have started paying interest in AI/ML integration, particularly in the field of NLP and LLM, because I find it is a great future. This is all about me, and let's dive into the topic. First, NLP workflow. This is quite generic. It's not required we should follow this workflow if we design our own NLP program. Like we can add our own steps and remove some steps. In like if I use BERT, I can eliminate the first step, pre-processing. Tokenization, ping, limitization is automatic if I use BERT embedding model. So it's up to us what we need. But our key focus is vectorization, word, sentence embedding. Here, the data or prompt we generate in our chatbot or our search criteria, it will be converted into vectors. And later it will be stored in a database or searched into a database with particular vector. What is vector? It sounds like a new term. Let's try to understand. A vector can be understood as an ordered list of numbers, or in a programming terms, it can be presented as a one-dimensional array of multiple numerical elements. This concept has been used in physics, especially in quantum mechanics, for decades. Those who work with quantum mechanics are well acquainted with that. But being IT professionals, this is new to us. We never thought of it before. You can see the diagram below. It represents a vector. Vector is just a point in a multidimensional space. We can see man, king, woman. They are just points. And the arrow we see is the direction. Vector can be two-dimensional, three-dimensional, and dimensional. The number of elements decides the size of vector. Like an example and diagram we see, they are three-dimensional vectors. But in reality, we would never see three-dimensional vectors in AI/ML. We would see 500 dimension vector, 50,000 dimension vector, or even 150,000 dimension vectors. Now, how are vectors generated? What is the process? Why do we need it? Let's try to understand. Why do we need vector embedding in place? First of all, why? WH, So here is an answer. When we deal with or we work with AI or LLM or NLP, we deal with unstructured data. It could be in any format like video, audio, text, images. If we use SQL, which is called structured query language, would we be able to glean required data from unstructured data? The answer is no. Simply no. So what should we do? We have employed a new method of vectors. It's more efficient for SQL. How to generate vectors? You can see the figure on the right-hand side. Vector embedding model in the middle. It receives objects and generates vector for those particular objects. Those objects could be anything. It could be text, image, video, audio, maps, coordination, any form. It receives object in any form and generates vector from it. But how does it compare? How does it understand? So here is an example. King minus man plus woman is queen. It says that woman with king attribute should be considered a queen. That's how vector embedding works. It assumes word and try to understand words and gives out output about it. Why do we need vector embedding at all? Is it really required? The answer is yes. When we deal with unstructured data, keyword search is not very effective. It may not give appropriate results. Let's try to understand that. I give two statements. I ate an apple, and statement two. I visited an Apple store. Apple is common, but semantic meaning differs. How? In the first statement, I said I ate an apple. That means apple was a fruit. In the second statement, I said I visited an Apple store. Here, Apple refers to a brand or company. With a simple keyword search, we won't be able to identify that. The apple is actually a company or is a fruit. Another similarity search. Similarity search are ANN algorithms. ANN stands for approximate nearest neighbors. If we have employed a different method for search, we need a different method of searching as well. We can't go with simple RDBMS SQL search. And to enable similarity search, vector methods are the best, vector embedding are the best method, or the best suitable candidate, in other words. Another thing is contextual search. I gave two examples. Now, if I add third example, an apple of my eyes. Wow, this has a completely different meaning. In this case, apple is neither a fruit nor a company. It's someone whom I like. So to understand and embed with a complex relationship or contextual relationship, vector embedding is helpful. We can use vector embedding in various applications like chatbots, agent AI, and even if you want to improve our search result in search engine, vector embedding is present. These are few vector embedding algorithms. First, we can see word to vec. It predicts surrounding words and embeds in such a way that surrounding words or the word we assume quickly should be picked first, like lion. So if we think of lion, what do we think first? Or what are the few words that pops into our mind quickly? Courage, bravery, cub, king, jungle. Those words would appear quickly, or those words should be picked so that search should be optimized. Another two we can see glow and fast tags. They are simply extension of word to vec. Bird is also kind of word to vec, but it's contextualized embedding, like I mentioned the apple oven. The same way if I say speed and full speed, they both have different context and different meaning. So the embedding or vector should be different for both of them. Clip is for text to image and image to text. We generate image and text in such a way that it can interchangeably be used for both. Wave to vec is for audio vector embedding. Like if we have audio, it will generate vector from audio. And the same with video to vec is from video to vector. Now, is it possible to generate vector embedding by our own? Yes, of course. We can design our own model. And if we have already designed model, we can install or set up in our own system and use it using our own programming. But let's say I can't afford a huge infrastructure cost. In that case, there are some options we have. We can use OpenAI API, Azure OpenAI API, and Vertex OpenAI API. Any of them are suitable. We can write the code in languages like Python, C, C++, Java, Go, anyone. We can just call API in programming language and generate embedding. Out of them, OpenAI API is very popular. We can consider a first move advantage. Azure OpenAI API use some same embedding models as OpenAI API has, and it has their own as well. Vertex AI API has the same model as OpenAI API, and in addition to that, it has its own module. Vector similarity search, these are ANN algorithms. These are most important for search. The exact is not ANN exactly because exact tries to match the exact vector. In theoretically, it's possible, but in practical, we don't see it happening because there are a number of vectors we have, and finding for an exact match is a little difficult or almost impossible. That's why we rely on cosine similarity, Euclidean distance, and dot product. What is cosine similarity? Cosine similarity measures angle between two vectors. Like let's say I search for foods. So what are the foods we have? Mangoes, apples, bananas, guavas, and many others. So a vector of fruit should have close and should have smaller angles with apples, oranges, bananas, and mangoes. But let's say cucumber, definitely not. So it should have wider angle. Cosine similarity is basically a good candidate for text search, genomatics, biometrics, and some more similar applications. Second is Euclidean distance. This is also known as alto distance. It it measures distance between two vectors. Shorter vector are close matches. This algorithm is used in case of maps or scalar distance. Like if I want to find distance between two locations in a map, image comparison. In such a case, it works better. Dot product generates multiplication of two vectors. Shorter one are close matches as others, but the use case is different. We can use this in case of image image comparison like including distance as well. Apart from that, it may help in decision making. Also, if we want to make recommendations, this is proven best. There is another use case. Let's say I have an idea and I want to generate a thesis from it. Dot product is useful. Throughout, we have understood the concept of vector embedding, vectors, vector uh, vector generation, but somehow we have to store the vectors and embeddings in there. And we need a spatialized product. It should be able to distinguish between vector and data. We have to store unorganized and unstructured data along with its vector. And it should be easily distinguishable. Also, it should support search methods like cosine similarity, alto distance, and dot product, and indexing for fast search. All those should be supported in some product. And the idea got materialized in 2000. we had the first vector database called Monad. After that, we also had some new few more products designed by some people, community or developers. But this idea gained traction in 2023 because uh, AI started becoming popular, and vector database were much in talk in those days. These days, vector database supports billions of vectors along with high dimensionality search. Now consider a vector requires a lot of space along with where the unstructured data is stored. If we want to use our own infrastructure, it's possible, but we get the optimal result or result as per the expectation or in time, it's highly improbable because it has been seen supercomputers are not even capable of handling that large amount of data and search. That gave birth to new concept called quantum computing and quantum computers. Quantum computers are still not ready to use in industries, but I'm sure it will soon become a reality. These are some popular vector database products. Out of them, Pinecone has been widely used. And nowadays, pgvector is the talk of town. What is pgvector? pgvector is an extension to Postgres. Now, Postgres has a beauty. If any feature is not supported, I can write a code by myself and attach it to Postgres, install it as an extension, and I can use it without any difficulty. Another thing is integration. I can write a code in Python or any other language, generate embedding, and store in Postgres. Now, what are the advantages of using pgvectors? We can use the same infrastructure. This exactly contradicts with the statement I gave earlier. But if I want to use at a small scale, I don't need to have another database or another server setup. It's easy. I can just install an extension and start working. Now, again, these two features are highlighting one. Support vector types and distance functions and perform PITR and data aggregation. Vector type and distance functions are features of vector databases. PITR and data aggregations are features that are provided by our DBAs. pgvector supports both of them. That's why pgvector is distinguished product. Data aggregation is not possible with normal vector databases. Like I want to perform sum, count, max, mean. It's not possible. Also, let's say I have removed some data accidentally or deleted some data accidentally. It may not be possible to retrieve data in some databases, but if you're using pgvector, you don't need to worry. You're safe. Yes, you need to take backups or else you're not safe. Another thing is support indexing and filtering like other vector databases. We'll shortly take a look into it. Besides the algorithm I mentioned, cosine similarity, L2 distance, and inner product or dot product, it also supports few more algorithms like L1, Manhattan distance, and Jacobian distance. Manhattan distance and Jacobian distance are binary search algorithms. The one open source and actively maintained is more important. In other words, I can understand that if I find a bug in the code, I can simply report it and developers will start working on it. These are indexes used in pgvector, IV flat and HNSW. Both has its own features, advantages and disadvantages. If we talk about IVF flat, it builds quickly, requires less memory and space, which is not the case with HNSW. But HNSW is very accurate in delivering data and query performance is optimal, exactly opposite to IVF flat. Another thing we have to take into consideration, we have to provide the algorithm we are going to use. Like if I create an index with cosine similarity, and I'm trying to search for, I'm trying to use L2 distance, the index would not work for me. So the index should be chosen wisely. We have to understand the requirement of a product or program or whatever we have and choose index appropriately. Because useless index would occupy the space and also kills our time in query. That's how querying pgvectors. First, cosine distance we can see order by embedding left arrow equal to right arrow and compare with vector. The same way we can see with repeating distance left arrow hyphen right arrow. For inner product, left arrow hash and right arrow. The limit file shows the top file result. The base file matches. There are some recent developments in this pgvector. Timescale came up with a new extension called pgvector They have designed a few innovations like streaming disk AN and SPQ. That has put them on podium because it performs drastically well. If we compare with pgvector performance, it's outstanding. Another extension designed by Microsoft Azure AI, it has a unique feature. Let's check an example. If I'm working with pgvector, I have to write a code in a programming language to generate embedding from API. In Azure AI, that has been completely eliminated. I have a function available. I can just call a function and generate an embedding. That's really a great achievement in these days. So we have reached the end of the session. I hope you enjoyed it. Stay tuned and thank you.